Okay, and then I forgot a little note that I wanted to put there that I said, but I didn't write down. I wanted to also note here, right, that the combinational logic, what we count, the combinational logic controls what we count to next, is the idea. Okay, it doesn't want to change colors, but that's fine. So the first step in our process is going to be to draw a state diagram. That's our part one here, because it's a lot easier for us to keep track of what's doing in what we're doing in a graphical format. We can go directly to a table if you want to. That'll be okay. But here we're going to draw a state diagram right now. So in our state diagram, you don't have to put them in numerical order or anything like that. So I'm just going to draw our circles. So we're going to have a 0, and then a 4, and then a 6, and then a 7, and then a 3, then a 1, and then we're going to go back to 0. So that's 6 different numbers. So you'll notice in this sequence that 2 and 5 are missing. We will be able to deal with that just fine. It doesn't add that much more complexity. So now I'm just going to fill these in the requested order. So the number 0 has the code 000. The number 4 has the code 100 in binary. The number 6 has the code 110 in binary. 7 is 111, and then 3 is 011. And 1 is 001. So you can see that once we convert it to binary, there's a little bit of patterning here. So it's not surprising, not altogether surprising, that it has its own name. So this would be a Johnson counter. It's slightly different from the regular Johnson counter, but it's very similar. It's a Johnson type counter, also called a twisted ring. But we didn't really look at that. You call them that when you design them from another viewpoint, but here we're just doing them as a regular counter. So this would be our sequence, and there are no control inputs in this case. There's nothing that changes the order that this counts, and so as a result, we just follow the sequence in order. So on every clock edge, we follow the arrow to the next count in the sequence, from 0 to 4 to 6 to 7 to 3 to 1, back to 0. I don't know why I wrote a 0 there. That's 0. 3, 4, 5, 6 arrows. Okay, and so this is our state diagram. And the memory is going to be these. We can either use D flip-flops or JK flip-flops. And so I will demonstrate both of those options once we're there. But we first need to start generating this table. So we need to generate the combinational logic which will control this memory. And so it will output the controlling signals for J, K, D, T, etc. based on the Q values, which is the only information it has to go on. We can see the present state of the memory. There are no external inputs, so the present state of the memory is all the combinational logic has access to. So we're going to have to carefully set up for J, K, D, and T. So to do this, I'm going to open up an Excel window. However, first, I wanted to set up the Logisim here. So I've got those 3 flip-flops that I said this was going to be made of. Controlling the flip-flops are the J's and K's, and then the output of the flip-flop, which contains the count itself, will be the Q values. So I've gone over here, and actually I meant to, well, it's fine. When we actually use it, we may have Q, Q2, we may have Q2, Q2 bar, right? We have access to Q2 bar, Q1 bar, and Q0 bar, so we will also be bringing those tunnels over here. But the idea is that the Qs go into the combinational logic and the Js and Ks come out in order to control these flip-flops and tell them how to change whenever the clock triggers on the edge. So now it's just a matter of designing this combinational logic right now. So back to the diagram and the table. So back to the diagram and the table. So we have various present states that theoretically we could be in. Not all of them are on the diagram, but that's okay. And so for any given present state, we will have a different next state that we need to go to, which will be specified by this diagram. So now it's just a matter of plugging in the relevant information. So this row says the present state is 0, 0, 0, which in our diagram is right here. The next state that we should go to on the clock edge, from 0, we're supposed to go to 4 here. So the next state is where this is going. Now, this you can do them in order. We can drop down here and say, okay, this is the row that accounts for 4. Where does 4 go? Well, 4 goes to 6, etc. The other way you can go about it is you just find that particular code on the list and you go from there. So this is 1. In this diagram, 1 is shown to go to 0, so we fill that information in. The code for 2 is completely absent from this diagram. There is no 2. It never counts to 2. 2 is never here, so we get to put don't cares in those cells because it doesn't matter what state we would go to if we were in state 2, because we'll never be in state 2 according to the diagram. So we don't care where it would go if we were there because we're never going to be there. So we just put some don't cares here. Then we have a 3. So in this diagram, 3 points to 1. So we fill in the 1. I already wrote down the 4. The 4 goes to 6. Then 5 is also not on this diagram, so we don't care where 5 goes. We'll never be there. This row says 6. 6 points to 7 in this picture, so we'll fill that in. And then 7 points to 3, so we'll fill in the code for 3. So the present state and the next state is now enough information to determine the flip-flop inputs that will make this happen. So this was the excitation table, and I showed how we derived this in class. So this excitation table comes from if we have a present value of 0 and we want the flip-flop to change to a value of 0 to keep the same value, the JK flip-flop, and it depends on what type of flip-flop you're doing, how you control its inputs to make the Q do what you want. But in the case of a JK, going from 0 to 0 can be done either by holding the previous value, which would be encoded by 0, 0 on JK, or we can reset, which forces it to 0. As long as we have a 0 now, either holding or resetting will successfully cause it to change to a value of 0 on the clock trigger, and that would be done with either 0, 0 or 0, 1. So as long as J is a 0, it won't matter what K is, Q will still go from 0 to 0. And applying similar reasoning, you can tell that to go from 0 to 1, you need to either toggle or set, which are 1, 1 and 1, 0 respectively. So all that matters is that J is a 1. You apply similar reasoning for 1, 0, you can either toggle or reset, which have a 1 for K, and then J wouldn't matter as a result. And then to go from 1 to 1, you either hold or set, and what's common with those options is that k must be a 0. So this is just the excitation table. You don't have to really worry about why it works, but that's the reason that it does work. And now it's just a matter of comparing value to new value. So that's why I've placed colors in my Excel table to make it easier to keep track of. So the excitation table applies to the same Q. You take the present value of the Q and you look at the next value of that Q, and that's how you apply this table. So this first one here, 0 to 1, this table says is obtained with 1x. This next row is a 0 to 0 change, and so that is a 0x. Since the destination here is don't cares, it doesn't matter what j and k are. Since we don't care where it's going, it doesn't matter what j and k tell it to do. This one is a 0 to 0, which we can fill in right there. This row goes 1 to 1, which is an x0, according to this table over here. 1x, so since our destination doesn't matter, we get to put that j and k don't matter there. 1 to 1 is an x0, and 1 to 0 is an x1. Then we run over to the green column, the q1 column. So 0 to 0 is a 0x. The next row is also a 0 to 0, so it's the same thing. The next row here, we don't care the destination here, so I'm actually going to run the x's all the way through, because for none of these q's does it matter where we're going next in the 2 and 5 rows. Okay, so back to the rest of the greens. 1 to 0 is an x1. The next q1 move is 0 to 1 in this table. Then we have a 1 to 1 in that situation, so that is an x0, and then a 1 to 1 here is an x0. In red, we go 0 to 0, which is 0x. We have a 1 to 0, 1 to 0 here, which is an x1. 1 to 1 here is an x0. 0 to 0 is a 0x. 0 to 1 is a 1x. And 1 to 1 is an x0. So this information is all that we need to generate our situation in Logisim. So let's pop that open, and then, not that one. That one can close. I want this one. Okay. Slide the table down here. So the next state is just something for our design purposes. The next state is not observable at any point. The combinational logic can only look at logical values which exist. So we can only observe the present state in this case. The next state is not a thing that we have access to. We can't pull a Q plus from anywhere. Q plus doesn't exist until the clock triggers, and then it will just be the new values of Q. So we can't use these for anything in the next piece, so I'm going to hide them. But we had to use them to generate the flip-flop inputs. So to generate the combinational logic we want, we need to output these J's and K's just using the present state. And so we'll have access to Q2, Q1, Q0, and these flip-flops will also easily give us Q2 bar, Q1 bar, and Q0 bar. So we're free to use those as well as we design our combinational logic. But the next move that we need to make is to solve the K-maps for these columns. And on the test, I'm going to want you to solve the K-maps by hand. I want you to be able to solve the K-maps by hand. So for this example, I'm not going to use Logisim to build them automatically. I am going to actually write down the K-maps for these, and we're going to solve them. So I'm actually going to cut this video here and split the final K-maps and build in Logisim to a separate video.